This talk, I'm going to say a bit about the vision that we have in ISG NGP, what NGP is about. And as you can see here, there are three main things. It was formed by some of the operators who had found problems with the IP-related technology and LTE. And with IP not really being very suitable for what they want to do. In particular, there was the issue that they have spent a lot of money on spectrum, and although 5G will get more bits over that amount of spectrum, they are saying that about, by some measures, 50% of those bits are unnecessary overhead. And so when they talk about application bits, they mean the real useful data for the application. I mean, there's a separate issue there as to how efficiently the application is using the channel, but that's somewhat by the by. If we can get rid of some of the unnecessary overhead at this level, then that will help. And the other problem with IP is that it's not really right for those, for the two things at the bottom of that triangle, massive machine type communication and URLLC. So those are the three things that I'm wanting to concentrate on in this presentation. The way of improving the current packet service so that you are not having as much overhead. And looking at a new service for continuous media, which will do what URLLC has been saying we need to do, and then how you get there from here. So looking at the traditional packet service first, and particularly looking at what's now published in our GS13, you'll get the slides afterwards, and in the last slide of this presentation there are links including to where you can download that standard. So this is what we call the basic service, which is doing very much what IP does. So store and forward with queuing, things having to go into buffers to be and queued up, and potentially the buffers overflow, and I'm sure you're all very familiar with all that. And with packets, sort of Ethernet-sized packets, and with transmission, it tends to be there's a burst of packets, perhaps when the user clicks on something, and then it's quiet while the user's reading what happened or what they got back. So IP is connectionless, and IETF have this religious belief that communication has to be connectionless. And one of the stories of the reason why it is that so that you don't have to keep state, and you think of what technology was like then, and memory was a scarce resource, and maybe that is that was an issue then. But actually, it's very unusual to get a packet that isn't related to anything else. Most data is either over TCP or over RTP, and those are streams of packets. And in a later slide, I'll talk a bit about the API as well. And memory is no longer a scarce resource. On the left there, this is something that we built in 1987, and it had 8K of SRAM. Now, actually, curiously, I didn't make that connectionless because we had enough memory to keep as much state as we needed for as many flows as it would carry. And not having to have globally significant addresses meant that we didn't have to keep state for those addresses. This actually is something on which a more recent technology was prototyped, or at least there was some initial work done on this, which is a board from Avnet, and that had 64 megabytes of DRAM, so 8,000 times as much. And then when I built the platform that the current technology was prototyped on, I used the smallest DRAM I could find, which was 2 gigabits. And so, memories really are bigger than they were then, and so keeping state is not an issue. And of course, we are actually keeping state in switches anyway. I mean, SDN is all about keeping per flow state. But in SDN, to identify which flow it is, you're reading these 5 fields that are down here in pale blue, and the switch has to read all those. It then has to look up in a table to find a match on that. And so our idea here is that actually all you need is a label. The label is chosen by the destination of the packet on that hop, and it can simply be the address in the routing table, which makes it beautifully easy to implement. Because you have it separate on each hop, that means you don't have to worry about what technology is used in other parts of the route that the packet traverses. And all the addressing is kept in control plane messages, which means that you can have new addressing schemes without changing the packet format. And you can experiment with other ways, again, that in this system. You could give a service name, or you could say where the unit was in the network. So there were lots of ways to identify what you wanted to talk to. And then the system set up the route to wherever. So all the per flow information goes in control plane messages. And I have to say that NGP has not at this stage looked very closely at what those control plane messages would look like. In the prototype, they are messages that are in this IEC standard, but other standards could be used, and I suspect that for mobile, something different might well be more appropriate. But what I'm mostly saying here is that you can get a lot more information into your control plane message than you can into your packet header, unless you're making your packet header really big, and then you run into the problem that operators want packet headers to be really small. It also gives you what I think is the right division of labor between what you run in CPU and what is in logic. Now it's something I find a bit difficult to explain in presentations, but this comes from having spent a very long time programming computers, and more recently programming FPGAs, and finding the difference between how you program something in an FPGA and how you program it in a computer. And finding that actually computers are really the right thing for the control plane, and they are not the right thing for the forwarding plane. Power efficient, this is referring to the way that in logic, if you want to test one bit, then, well, that's kind of one transistor or one logic gate. Whereas in software, if you want to test one bit, you need an instruction. The hardware decodes the instruction, and it will no doubt take 32 bits or 64 bits and select one of those and test it. There's a lot of switching going on in your electronics compared to what happens if you're doing it by logic, and that's why logic uses less power. On the other hand, it's much less flexible. I think that's in a later slide. Yeah, so again, this board actually doesn't have a hardwired processor, or, well, I think there's one in that interface, but it doesn't have a hardwired processor in the part that you actually play with. On the other hand, there's enough logic in there to have a soft processor, and those are quite fun. But in software, you've got processors competing for CPU time. And this is good for kind of non-trivial amounts of calculation, such as you will do when choosing the routes that a packet will follow. And of course, it's much more flexible. You can just get another piece of software and simply download it and link to it, and it runs. Whereas in logic, yeah, you've got to redo the place and route, and that is a bit of a pain. But for things like forwarding packets, particularly when you've made your packet format so simple that you're not expecting to have to change it, then it's much more efficient there. And as I've shown here, all the different processes all run at the same time. So the data goes from one to another, and they're all running continuously in a flow-through architecture. So you don't have the issue of having to get stuff in and out of the same memory. So memory interfaces aren't the same bottleneck that they are with code. And here I'm just showing that in this header, it's good for storing in memory and processing by software, but really you shouldn't be wanting to do that. But your software can, it can look at this a bit and then look at that bit and then look at something down here. Whereas if it's something that the logic is looking at as it goes past, then you really don't want to be doing that, because you have to store bits that you've seen that you don't want to use yet. And you finish up saying, okay, actually we are just doing this in the CPU-like way. You tend to finish up actually building a special purpose CPU to do it as well. So this is where I think of it as the steam age. You have all these headers on the front, all doing rather heavy stuff. Whereas if you're just label switching, then so much more of your train is actually able to carry passengers. Okay, second, what we've done for continuous media. Now again, this is in GS13, and this is the what we call the guaranteed service. Those of you who remember ATM might like to call it constant bit rate or defined bit rate. And it's for all these, as I've said, continuous media like audio, video, and these new ones like tactile, and the position of vehicles which are signaling to each other where they are, where latency is an issue. Now, obviously, you can You can use the other kind of service for this, but it gets horrendously complex. I think there are 14 different standards involved in TSN, and it still doesn't get the latency as low as we get it. So this is the synchronous service, and around 10 microseconds per hop in the prototype, which was using gigabit Ethernet as the layer 1. So we were using gigabit Ethernet PHY, although we weren't using Ethernet packets. And we get 10 microseconds. If you're running at 10 gig, then it will be 1 microsecond, so it scales with the rate. And obviously, if we can get 10 microseconds per hop in the core, and you've got 1 millisecond in the radio, then you've got only slightly over 1 millisecond for the combination. And in order to do this, the word synchronous, I'm very much using the definition that's in IETF DetNet's architecture document. There's a link in the slides to their current draft. It's going to be an RFC very soon, so that link will become obsolete, but they've gone into quite a good analysis of what the problem is, but they then have their hands tied and they can't use the kind of solution they do. So you need to have your frame, again, I can't go into the detail of this, but there's a link to where you can read it up at your leisure. But there's a very simple mechanism for doing the frame alignment that you need to do. And we also, in the frame format, we distribute time in the way that's needed, so you don't need a separate protocol for that either. The way it's done is that each flow is allocated slots. Someone was talking about being on rail, and this is very much like train timetables. So each train in the timetable has its path through the network. And of course, those paths are arranged so that things don't conflict at junctions. And we do it very much like that. And of course, because you know which slot something has been allocated, you don't need a label and because things have their own slots, you don't have to do policing or shaping, because that just kind of happens automatically. We're not restricted to 75% of the link capacity, as most other ways of doing this are. But where it's different is, some of the history of this is in ATM, and I really tried hard. I tried really hard not to have things that look like ATM cells. But it does turn out that fixed size slots work best because they make it easier to do the allocation. The packets in them, of course, are variable length, so we don't have the issue that ATM has there of actually wasting. And then if you can't get everything synced up, then you can do it asynchronously. Again, this is DetNet's definition of asynchronous. And on wired links, the way it was done in the prototype implementation, the basic service, the one I talked about first, simply uses all the space on the link that isn't actually used by the synchronous service. So if you've got a slot that's got a 10-byte packet in it, the other 54 bytes are part of the byte stream that carries the basic service. Okay, so how do we get there from where we are? I said that the kind of packets you have in the basic service, they're the right size and everything that you can simply encapsulate an IP packet in it. Again, there's an RFC for how you do that in ATM 1577, I think. And it's a very similar idea, and again, it's pretty much the way that MPLS carries IP packets. You can also use IP addresses as the addressing when you're setting up a flow that will then use the basic service without the IP header, because the IP header is basically in the it's per flow. The information there is per flow, not per packet. We can also do this the other way round. We can carry either of those services over UDP or directly over Ethernet. Also, it's a good fit with the sockets paradigm. You think not just sockets. IETF has a project called TAPS, which is looking at a more modern API that doesn't make the application commit to using a certain protocol. And but in that one, just as in sockets, you create the socket, you say what you want to communicate with, and then when you want to send a packet, you supply the data and the socket handle. And of course, in our case, the socket handle simply translates into a label, because the socket handle, again, is the identification of a flow. You can read the rest of this. Okay, so those are the links which are you will get when you download it. This is the our home page. There are 4 tabs on that page. Specifications tab has the specifications, has the standards and reports. The second of the tabs has our vision, and there's a blog tab, which again has got some background. There's a deep dive into the technology, and I've noted here that the basic service was called the IT service then, because it's for IT stuff, and the guaranteed service is for AV stuff, audio, video, and so on. But we decided that those were better names in one of the meetings this year. This one is TR29181. That is the output from a study in JTC1SC6, which are the people who brought you OSI, on future networks, which is about 10 years, it's 6 years old now, but the work had been going on since 2007. This one is something that I wrote for the European Future Internet Project, although I think they are not really looking at layer 3, they're only looking at layer 7. And this is on UK 5G, is the 5G Innovation Network, not to be confused with 5G IC. Again, that's kind of an explanation of where we're coming from. Okay, questions?
So just first of all, you talked about the weaknesses of computing or processors versus FPGAs. There's a lot of talk at these sort of events like this week from Intel about innovations like DPDK, which enable you to get more processing, more packet pushing capabilities from processors. So do you still not agree that processors like x86 based processors are suitable for the data plane? And then I had a second question.
I think if you've built your data plane right, then you don't need to do it that way. But yeah, I mean, I wouldn't want to be using an x86 processor to look at every packet, because I think all the things you would do with that are actually per flow. And I mean, what we've done here is a kind of simplification. We've said that we can very simply make this kind of service, and we can very simply make that kind of service. And actually, anything that you want to do is a good enough fit with one of those that you don't really need to do anything else. But yeah, I mean, it's something that hasn't been tested nearly enough.
Okay. And then the second question or observation was, made a couple of references to ATM.
Yeah.
We're not using ATM today.
No.
So why will it be different this time round?
Firstly, I really am not saying we want to go back to ATM. What I am saying is that there were good things and bad things. There were some things they got right, which were mostly technical. There were a lot of things they got wrong, which were mostly not technical. I mean, things like they were saying you need to have your ATM core, and then you need to have ATM devices around the edge. And only then will you be able to get the good service. And I think it was 1997, when they'd been going for 8 years, they came up with cells in frames, which was saying, actually, round the edge is not where the problem is. So why don't we just put that over whatever hardware is there, which is what I was saying in one of the earlier slides. So it's things like that. And, you know, again, in 1989, fixed size cells was kind of about as much as you could do with the hardware that we had then. Whereas now you can make your hardware a bit more complex and do things like having variable length packets and and saying, okay, here is our guaranteed stream, and it's using these bytes, and here are our basic service packets all queued up waiting, and we take a byte every time we've got a space, which means we don't need fragmentation headers, and the whole lot gets more simple there. And you're now using the whole space. You're not worrying about packet shredding, and you're not doing packet shredding with your IT stuff. You're only using small packets with your audio and video and so on, which, if you're taking this from your audio A to D converter, or you're taking it from your digital video input, then actually, just chopping it up is very simple to do again in the logic.
Thank you.
Yep. If you want to use the mic.
Do you want to use that one?
The industry IoT type applications. I think as for industry IoT, we're talking about low latency and high reliability. If you use the packet domain like IETF type things, probably is from real-time performance time, it's really difficult. And each hop, then you have the delays, right?
Yeah.
And another thing is restricted for the manufacturing process. Basically, you should not allow any delays. A lot of things is just a status change. It's from 0 to 1. It's like a switch.
Yeah.
That needs to be extremely reliable.
Yeah.
So how the NGP try to target this problem?
I mean, that is with the guaranteed service. The synchronous service allows you to, I mean, obviously, you still, if you're saying, you know, when should this switch happen, you need to be sent, if you want that switch to happen, you know, to the nearest half millisecond, then you need to be sending a packet every half millisecond, obviously, unless you've got forewarning of when you want the switch changed, and you can put a time in it. But we do distribute time to within a few tens of nanoseconds, and the time of arrival of the guaranteed service packets is fixed to within that kind of tolerance.
Especially for the manufacturing process, and sometimes they need a very accurate timing coordination. That means the event has to be happen exactly. Basically, doesn't give much time to the errors on the timing. So how to make this timing synchronization things really on the multiple process aligned together? And you can have fixed delay, half millisecond, 1 millisecond, 2 milliseconds, but everybody has to synchronize that kind of time scale, right?
Yeah.
And it doesn't allow any variance.
Yeah, the way the frame synchronization is done is, or in any node, you've got one incoming stream that's your reference, and you start the outgoing stream when a certain byte in that packet arrives. So that gives you a very tight synchronization. If you're wanting to say, okay, we have a latency of 100 microseconds across the network, but we want to be absolutely sure we get a latency of exactly 500 microseconds, then obviously your packet format needs to include the time at which you want the change to happen at the other end, and then you can do the alignment.
Okay, thank you.
Any more questions for John? So let's thank our speaker one more time, please.